Hello, and welcome to our second video on probability for Grade 12 Essential Math. In this video, we're going to take a look at theoretical versus experimental probability. These are ways to look at probability from a little bit different side based on whether or not something has happened or whether we know enough about it to predict what will happen based on what's possible. So let's take a look at an example to start off with. So here, I have three different types of dice. This first one is what I would call a normal die. So this here is one that has 6 sides on it. You can see that there are 6 different sides. They have 6 different numbers on them. So I'm going to call that a D6. Now this here, if I want to roll a 6 on that, the probability of rolling a 6 is pretty straightforward. 1 out of 6. One side, and it has 6 different, there's one side that has a 6, and there are 6 different sides on this dice. Now, this die here is a dice that has 12 sides on it. So this one here is what I'm going to call a D12. So what's the probability of rolling a 6 on this? Well, if I find the 6 there is one side that has a 6 on it, but there are 12 separate sides. Now this is a D20, or a dice that has 20 separate sides on it. So this one here, I want to say, what is the chance of rolling a 6 on that die? I've got one side has a 6 on it, but there are 20 separate sides on it. This is my theoretical probability. So my theoretical probability is based on what is possible. So this here is, if I were to write this out, the probability for theoretical would be options wanted or asked for. So we said, hey, what's the chance of rolling a 6? Well, there's one chance of rolling a 6, and that is over the total possible options. So in other words, there are 6 sides, so there are 6 possible options here. Out of that, I only want one. Here, there are 20 possible options, and I only want one of them. This is theoretical probability. Now let's try a little experiment here. I take my D6 here, and I say, I'm going to roll this a couple times. So I rolled a 3. I'm going to write these down. I roll this again. Oopsies. Roll it again. There's a 4. I roll it again. Oh, there's a 1. I roll it again. There's a 5. And I'm going to do this a couple times. Oh, there's a 6. Roll it again. There's a 3. 2. 6. 3. 3. 4, and one last time. I rolled a 1. Okay. Now, this here, I have done this. I have tried this, so these are my tries. If I were to say, based on the data that I've done here, what is the probability of rolling a 6? Well, I can look through here and go, well, there's 1 6 here. There's 1 6 there. So I have 2 out of 12. So this is my experimental probability. And this is based on something that I have tried, that I have observed in the past. I have seen this happen. So another way of writing this is my probability for experimental is tries that resulted in the thing we want or the thing we're looking for, divided by or over the total number of tries. So how many times did we get what we wanted or what we're looking for, divided by how many times did we try in total. Interestingly, this here, 2 out of 12, is the same as 1 out of 6. So my experimental probability and my theoretical probability are the same in this case. However, that does not have to happen. If I say, what's the probability of rolling a 3 based on this data? Well, 1, 2, 3, 4. I got 4 3s, and I tried 12 times. Cool. What's the probability of rolling a 5? Well, there's only 1 5 out of 12 tries. So experimental probability might be different than the theoretical probability because our tries are different there. Now, if I stop my experiment too soon, I might get weird probability, and that might not work out very nicely. For example, if I take this dice, so let me roll my fancy clear D20 here. If I roll this and go, hey, I got a 3. I'm going to roll it one more time. Oopsies. There we go. I got an 18. If I stop here, I don't have enough tries to really say anything. So with my D20 tries here, I could say the probability of rolling a 3 is 1 out of 2. But that doesn't make sense, because if I keep rolling this, it's probably not going to be half the time I get 3s. It's not going to be half the time that I get 18s. If I say, what's the chance of rolling a 20? Well, I didn't roll any 20s, so the chance of rolling a 20 is 0 out of 2. And that doesn't really work very well. So I did not do enough tries here, so my data isn't good. This can be seen in the real world when you don't have enough people for a survey, for example. If I do a simple one, like say, I ask people where their favorite pizza comes from, but I only ask one person. And that person says, my favorite pizza is from Niagara Pizza. Great. Except I've only asked one person. I don't know what the most popular type of pizza is because I've only asked one person. And you can see this in the real world when people bias data, and you'll see it in the news as well. If they don't ask enough people, they might not know what the real answer is. If they don't ask enough people who they're going to vote for, they might not have good data for an election. If you don't ask enough people what sort of product they prefer, you might not have good information based on that to tell what you need to stock in your store. So the number of tries that you have for your experimental probability is really important, because for some things you can't do theoretical probability, or the theoretical probability might not match. How many people prefer Coke to Pepsi? That depends on who you ask. You need to ask a lot of people to get a good result for that, because it's probably not split 50-50 either way. I hope you have a great day, and I'll see you in the next video.